Okay, so loud. Okay. In today's lecture, we are going to cover some knowledge about gear design. So let me make sure I have the right slide. Okay. I only have today for gear design. So I'm not going to cover too much. So if you are very interested in gear, I highly recommend you to take courses from Professor Shi Yipei, Professor Shi. She is the master of gear design. Okay? Now, there are several kinds of gears. Spur gear. If you have spur gear with the teeth aligned in a helical way, like a helical curve, that is called a helical gear. And if you have the gear shape looks like an umbrella, it's called a bevel gear. It's like a cone shape. And the worm gears usually is named based on the shape of this one. This is like a screw, it has a helical curve as well, and when it rotates, it looks like a worm. So that's why it's called a worm gear. Okay, so you can see this in your oscillating fan. Do you know inside an oscillating fan there is a worm gear? Okay. So take this one as an example. Here. Oh. So the blue one is actually a worm gear. So the motor is where? Motor is at the, let me see, where is the motor? Oh, this is the motor, right. This is the motor. And basically it's spinning the worm gear, so this purple gear spins as well. That allows your, so it's generating some kind of rotational actuation, and there is a 4-bar linkage inside. So that driving force is gonna drive one part of the 4-bar linkage. So the other part become a oscillating motion. So that's why your fan is able to oscillate when there's only one motor. So it's oscillating not because the motor rotate clockwise, then rotate counterclockwise. No. The motor spins in the same direction all the time. And the way this oscillating fan is being able to do this motion is because of this mechanism. So the motor is being attached to this yellow part. So this is always spinning. And this blue part is oscillating. Okay? Another reason why people use worm gear right here is to reduce the speed of the oscillating motion. If you directly use your motor speed applied to the 4-bar linkage, then it's gonna oscillate so fast, then it's gonna be too crazy, right? So that's the most common 4 kinds of gears. And of course, for the bevel gear, sometimes when they are looking for stronger payload, they even have helical curve of the teeth. So for the bevel one, they have cone shape, and they also have helical teeth. Then that allows the driving force to change its direction. Like for example, you have a motor right here, you are driving in this way, and the other part is being driven, and the driving axis can be different from the driven axis. So that's where you use a bevel gear. And sometimes when the driven one is carrying different kinds of loads, maybe there is a reaction force applied to a certain direction, so it's not good for the teeth. So sometimes they want to generate helical shape of the teeth so that the teeth can carry forces from different directions. Okay? Now, there are some names you need to know. The distance from one edge of the teeth to the other one, exact same position, is called a pitch. And usually the pitch is being calculated around a pitch circle. So where is the pitch circle? Pitch circle is like the position where you assume there's interaction of forces. So when you design gears, for spur gears, for example, you have a bigger one and a smaller one, and you assume there is force being applied from one side to the other side. And usually the force is like not following the tangent direction, and also not following the exact actual direction. It's like having an angle, okay? So you can think of the teeth is like this, and the force is being applied on this point. And this is the pitch circle. So whenever gear designers are trying to design the size of the gear, how many teeth, they use this important dimension to compute the size of the gear. Okay? And since there is a direction, so they want, whenever there is a so-called conjugate motion between the gears from both sides, then the gear on the other side would look like this. Okay? So there's a perpendicular force being applied from one side to the other side. That force vector is aligned along this like a pressure line. Okay, so the force is always coming in from certain angle. So let's say when the gear moves to the other configuration, for example, this configuration, and the other side will have a different motion like this, and the contact point remains on the same line. So this force transmission stays in a very stable direction all the way when two teeth conjugates with each other. When they have a first contact, they keep on contact until the end of this connection. along the way, these two conjugating teeth are always having the force transmission along the same direction. Okay, so the profile of the teeth is being designed in a certain way, so this is happening. This constant force along certain direction is happening. Okay, and I'm not the expert of designing gears. I'm not going to tell you how they did it, and the course is not about this. You just need to know the names. Now, usually they call this part as the face and this part as the flank. Okay, on the side of the profile, separated by the position of the pitch circle. Upper part is the face, the lower part is the flank. It's like the upper part of the teeth and the lower part. And the width of the teeth is called the face width, because this is the face, then this is the face width. Okay? And sometimes people call this upper part addendum and the lower part addendum. Okay? They're just names. I think that's everything you need to know at this slide. No, there are some equations. Since we're not doing homeworks, we're not going to try to compute certain things. There's just equations for you guys. Maybe try to understand there are certain important terms for designing a gear. Of course, you need to know how many number of teeth you have. So n is number of teeth. And like I said, there's a pitch circle, the diameter of it is the pitch diameter, the small d. And there's a unique parameter called the diametral pitch. What does it mean? It's the ratio of number of teeth over the pitch diameter. So it's like per pitch diameter, how many number of teeth you have. So it's called the diametral pitch. That's the definition of it. And the inverse of it is called the module. So usually those numbers are given by the manufacturer. Because the way the gears were being manufactured is not so easy. It's not like you have a CNC machine, and then you design how you cut, how you make the cuts, and then you have your gear. It's not like that. It's not that easy. Because if you have if your cut is not precise enough, then the profile may not conjugate well enough with the opposite teeth. Then you don't have a very smooth motion. So usually there are many ways of making gears. There's one way of making gears is by a tool that looks exactly like a gear. So it's like a cutter that has a gear profile, and it's like removing materials away from the outer edge of the like a cylinder. So it's all constantly cutting, removing some material at those corners. So whenever it removes the gap between two teeth, then you have the teeth profile. Okay. So it's impossible. It's very difficult for the manufacturer to prepare the cutter in all kinds of dimensions. That's why they have these calculations and claim, okay, now I am designing a gear in a module number of 1 or 1.5 or some number. So they can prepare a certain set of cutters or tools to manufacture those. So it's usually very difficult for you to find gears with characteristic parameters that is not found from the manufacturer's data sheet. They usually give certain numbers to those values, like these. Like this book is supported by one manufacturer. They only prefer to have certain numbers of modules. They don't want you to design gears in different numbers of module, because usually you cannot buy them. You don't see them. You don't see them in the market. If you don't have them, maybe you can only manufacture by yourself or 3D print by yourself, and the quality may not be good enough. Okay. The other number, small p. Small p is the circular pitch, the distance that I mentioned from here to here, the arc length from this point to this point. So basically is the parameter divided by the number of teeth, right? So over here, pi d is the parameter and divided by number of teeth. Then you have your circular pitch. Okay, so those are like very fundamental numbers for gear design. I'm moving on very fast. This is trying to describe the conjugate motion, and you can tell they draw a line right here. That's exactly what I mean right here. Okay, the contact between two teeth and how the force is being transmitted from one side to the other side is always aligned on a straight line. So whenever there's a gear conjugating motion, this force transmission is smooth, stable. You don't have change of forces. And this is how, based on the goal of having constant force, pressure line, they have to design the profile by so-called involution lines, involution curves. I'm not going to explain this, but if you truly take some courses about gear, they should cover this. In my course, I'm gonna quickly move on to the most important part of this course. This is exactly what I show you right here. Okay? A and B represent the starting and the ending of their conjugate motion. So imagine if gear 1 spins clockwise. So when the teeth comes to here, when this particular teeth have conjugate connection with the other part, the opposite teeth, the first contact point is an A point. From now on, whenever the gear 1 continues to spin, the contact point moves along this straight line until it reaches point B, and that's where this connection finishes. Okay? So they sometimes also study how long the conjugating teeth connect with each other. If this connection is quite short, then your conjugate motion may not be smooth enough. Because when this pair of teeth connects, and when it's about to finish, you want the other pair of teeth start to conjugate. Right? You want multiple pairs of teeth conjugate with each other. Then you have very smooth connection. Okay, moving very fast. So this is describing the whole exact same story. Now, there's a terminology called rack. So they usually call these kind of gear pairs rack and pinion. So this is a rack and this is a pinion. What is a pinion? Pinion, whenever there are two gears connected with each other, they call the smaller one pinion. So you usually hear people say gear and pinion. That means you have a pair of gears. The bigger one is called the gear, the smaller one is called the pinion. Then how come this is rack and pinion? Can someone tell me? Why do we call them rack and pinion? Why not rack and gear? If this is a rack, the horizontal one is a rack. If you have a gear in this shape, like a straight line, that means the diameter is infinitely large. So it's a super large gear. That's why the pairing one is a smaller one. That's why if this is called a rack, this is not called a gear, it's called a pinion, because it's the smaller one between both. Okay, so rack and pinion. You always hear that, but you don't know why. Now, it's sometimes very important to calculate the pitch. So, from previous equations, we were able to compute the arc length from here to here. But we also need to know what would be the pitch from here to here for the rack. And the pitch sometimes can be studied in a different direction. So for the rack, this dashed line is actually the pitch circle for this rack. So this is definitely its circular pitch. But if we study the shape of the teeth, we can kind of study in a different orientation. And over here there's a tilted line. This is basically the pressure line. If we observe the pitch along this line, then there is another way to study the distance between the first teeth and the neighboring teeth. Then there is a pitch analysis along this way, and this one is called the base pitch, okay? Because this line is tangent to the base circle, I think. Yes, tangent to the base circle. But I didn't cover what is the base circle, so forget about it. Just there's a circle tangent to it, and that's called the base circle. So this one is called base pitch because it's a different way to observe the pitch of a rack in a different direction. Okay, because those dimensions are important. You need to know what's the distance between one teeth and the other one, so you don't make an incorrect gear. Now this is called the internal gear. Okay, so basically for the internal gear, the shape is like an opposite shape. The teeth shape is like matching the groove right here. Okay. So now those are actually not the most important thing for gear design, but those are like fundamental knowledge. For helical gears, since the profile of the teeth are following those helical curves, so there are multiple ways to study the pitch. So when I taught this course in the past, the most troublesome part to study the pitch is that you have to observe the teeth profile from the side of the helical gear, and you realize this stripe could be on the top of the heel, and the other stripe is at the bottom of the groove. So top and bottom, top, bottom, top and bottom, right? So whenever you climb the mountain, go down the mountain, and then climb again, then the distance from one edge of the mountain to the other edge, to the second mountain, that's a pitch. Right? But the way you climb it, you can follow a different direction to climb the mountain of the teeth. Then there are 3 different directions that you can do it. Let's focus on the horizontal one. So here, this figure, if you try to find a point, so let's say this stripe at the right edge over here. This is for example, the starting point of the mountain. So this is like a mountain going down, and this is the groove, and so this is another part of the mountain. Then it stops at the same point. Then the distance is the pitch. And they use PT because T represents transverse. So it's like a transverse direction. Okay, so this is PT. If you study the distance along this transverse direction, horizontal direction, then this is PT. Now, similar to what we mentioned earlier about the angles, but this time they try to tilt your head and then try to observe the teeth along this way. And the angle of your tilt is exactly the helical angle. How much tilt you have for your helical curve. So when you tilt in this way, then when you observe the teeth, it looks like a spur gear. Okay? So if you tilt this way and then you try to study from one edge of the teeth, going up and down, and then move to the other one, then the distance right here will be the pitch along this direction. And since over in this direction, the way you take the walk is perpendicular to the direction of the teeth, then they use Pn. N represents normal. So it's normal to that direction. So over here it's called the P normal, Pn. How about Px? X represents the direction along the axis of the gear. So the axial pitch. How do you do it? Basically, you take a walk along the axis, and when you see a pitch, one edge of the teeth, going up and down, and then when you're about to go up again, that distance is Px. So X represents the axis. Okay, so in this part, there is a bunch of calculations for this, just for you to know. For helical gears, you need those calculations for pitches along different directions. Why are those important? Because later on, what we care the most is about how the force is applied from one side to the other side. We care about how much load the teeth carries. If the load is too large, the teeth can break. In this course, we care about how much load a gear can carry. Before you try to analyze the stress inside the teeth, you have to understand where the force comes from and from what direction. That's why those information actually is quite important. Okay? Now let me move on. I need to move on to this is like shaping. This is so-called a pinion cutter. So the cutter on the left has a gear shape, and it's a smaller gear shape, so it's a pinion. So basically, it's like a gear-shaped cutter, and it's making cuts on the outer edge of the cylinder to form the shape of the gear. Okay? And there are a motion called hopping. So we have small cutters like the over here, and then it's like making nonlinear cuts to form this worm gear. Anyway, now bevel gears. Here is the part that is a little hard to understand what's going on. So I need to jump out of here and then remove these two. So let me remove these two and then I will explain what's going on. So for the bevel gear, they are like umbrella, they're like cone shape. So how do you study, because you know it's on a cone. So whatever we talk about in the past cannot be directly applied to what's happening on the surface of a cone. So it's very difficult for us to take something over there from the previous slides and then use it to study whatever is happening for the bevel gears. And people figure out a way. When two bevel gears connect with each other, they still have similar conjugate motion. And the profile still looks a little bit like the spur gear. So they treat the local area right here just like spur gears, the circle ones. But how do you compute the size of everything? They generate so-called virtual gears. So the local conjugate behavior behaves exactly like two spur gears, virtual spur gears, where this one is having a center right here, the other one is having a center somewhere here. So the way the teeth are conjugating with each other still looks like spur gears. So they use this way to compute the virtual spur gear teeth number. Okay? So this is quite different from the spur gears, but they still treat the conjugate motion just like the spur gear. Okay? That's why I draw these two virtual spur gears right there. Anyway, there are some tangent calculations to compute the ratio between number of teeth. P represents the pinion, G represents the gear. So the bigger one is the gear, the smaller one, again, it's a pinion. Anyway, let me continue. Similarly, for the helical gears, if you stay on this tilted direction, the teeth behaves just like a spur gear. So whatever calculation along this tilted angle, this helical tilt, you can use whatever equation you had for the spur gear along this direction. So that's how they use it to compute some of the equations from different directions. Okay, let's quickly move on. The worm gears. Worm gears, not much I want to talk about. Basically, again, there are some calculations about the pitch, but I don't want to spend too much time. And usually for gear design, there's a train of gears, and there are quite important calculations over here, but again, not the most important thing in this course. But if you later in the future design gear trains, then usually you need to compute the ratio of number of teeth in a series. Then you will know the efficiency of your gear train. Anyway, I think this particular slide is done. Here. Here is what is truly important for this course. So take the pair of spur gears as an example. We want to study where the loads come from. So let's focus on the gear, which is sub-figure C. Right here, since the pinion is going to have a force applied to the larger gear. So there is a force F23, so this is gear number 2, gear number 3, so there is a force 23 coming from the teeth of the pinion applied to the teeth in the gear. And like I said, it's always following the same direction with a pressure angle. So in order to have a balance of force, at the center, that's where your gear that is installed on a shaft. There's always a shaft. So there's a reaction force at the center of the shaft. Assuming there's no other forces, then the reaction forces must have the same size, exactly opposite direction. So you have balance of force. However, it doesn't have balance of moment yet, because two exact same size of force coming from opposite direction and doesn't stay in the same line, it's so-called the couple, right? It's a couple, force couple. So whenever you have a force couple, that's generating a moment. So in order to have balance of moment, there must be a response moment, reaction moment. We have reaction force, we also have reaction moment, like a reaction torque. So because of the force coming from this pinion applied to the gear right here, on the shaft, you will have a reaction force coming this way. Due to this couple, it's generating a counterclockwise moment. So right on the shaft, it's gonna generate a clockwise reaction torque to balance with the external force. So on the shaft itself, not only there is a reaction force, there's also a reaction torque. Okay? So think about what we learned in the very beginning. We have a shaft system. If there's a gear, it not only needs to carry the force, it also generates torque. Okay? Similarly, on the opposite side, there's also torque right here. And this torque is balanced with the moment generated by the couple. Okay? And of course, these two are the same. Same size, opposite direction. No matter how much force I push you, you are going to push back. Same size of force. Opposite direction. Okay. Now, later on, when we focus on the force that is applied to the teeth, the most important part is actually the transverse component of that F32. So F32 transverse will be applied to your teeth. So all the time, your teeth is gonna be pushed with a transverse force. 32 transverse, right? So for the teeth itself, the teeth is like a cantilever beam. Cantilever and being pushed down at the edge. So the teeth could break. So whatever we learn for beam, force analysis for a beam can be somehow applied to the teeth. But the teeth doesn't have a constant cross section. So the analysis is quite different. I'm gonna show you what's going on. Okay, so this is like a gear train with 3 gears in different sizes. And take a look at the gear number 3, which is shown on the right hand side. You can tell in this way, in this particular situation, gear 4 is pushing gear 3, and also gear 2 at the bottom is pushing gear 3. So for gear 3 itself, the force is being applied from both sides of the from both sides of the pinions. So at the center of the gear 3, there's going to be reaction forces. So for this kind of particular situation, you have to do real calculation in order to figure out whether there's balance of force and also balance of moment. Okay. So this part is telling you how to calculate it. So usually for a shaft system, you usually have to design for the gear pairs, study the force being applied between the gears, then study the reaction on the shaft, and then go back to your shaft to figure out how much force is being applied to the shaft. So that shaft, you need to do whatever we did for the first couple of weeks. You have a shaft design, you have shear force, moments, and so on. Okay, then you know whether the shaft can carry the loads. So here's the complicated part. When we analyze the bevel gears, what's happening is the teeth profile stay on the cone shape, and since the profile is along certain angle, so you know the force coming from the opposite side of the teeth is gonna perpendicularly apply to the teeth profile on my side, and that force vector is coming from certain direction. It's not parallel with any axis in your gear system. So over here is telling you there are actually 3 force components for that pushing force. So they label those 3 components as W, T represent the transverse direction. So how come it's the transverse one? Because if you observe this as a pitch circle, then this is like a tangent direction. So they treat that tangent direction as the transverse direction. And WR represents the radial component. So basically, the direction that is parallel to the radius. And also the other one, WAA represents axial. So the direction along the center of axis of this gear. So for spiral gears, if you try to study the force applied to the teeth, you always need to compute the force components along all three directions. Okay, next. This is a problem that usually when I taught this course, I ask students try to solve it. I like this problem very much because not only you need to understand about the gear and pinion pairs for bevel, gear and I should say bevel, gear and bevel pinions, and also you study something about the shaft. So what's happening is this particular force diagram is representing what you see on the upper left corner. So over here, let's try to observe everything by the symbols. D is this one, so there's the cross represents a bearing. There's a bearing right here. There's another bearing at C. So you have reaction forces from the bearing. So there's where you have two bearings. And actually in the problem, it tells you there's a thrust. There's a thrust force applied to the bearing, but only bearing C is carrying the thrust. What kind of thrust? It's like there's a driving force that is driving the pinion, and there are forces pushing away the bevel gear. So if there's force pushing this bevel gear, you need something to carry the force. So that's a thrust. And that thrust is being carried by the bearing at C. So over here you see a FC along this direction, but this one doesn't have it. So whatever thrust that is being generated by the driving force from the pinion is gonna carry by C. So there's a reaction force here, okay? Over here, what is the point G? Point G is right here. Right at the, like a pitch. Actually, it's a pitch circle right here and another pitch circle right here. The contact point of the pitch circles. That is the point G. And over there, you can see there are force components along all three directions because they are bevel gears. So you have force components along all three directions. So for this particular problem, it's trying to study the shaft. So for the shaft, you actually have some forces that is not exactly applied on the shaft itself. It's actually having a force applied somewhere outside. So for this shaft system, the force comes from here. Okay? So that's, for example, this WT is gonna generate some kind of moment. So the torque right here is going to balance with the moment generated by WT, right? Then you can compute how much torque that is generated right there. Okay? So that's pretty much I want to talk about. I can give you the slide later on, so if you're interested, you can just jump in to take a look. This is about the helical gear. Similarly, because of the helical profile, so the force coming from the opposite side of the helical gear is following certain angle, and it's gonna have 3 force components. Again, WT represent transverse, WR along radial direction, WA along the axial direction. So it's quite similar, so I'm not going to cover those. This is for worm gear. Again, for the worm gear, the force, the profile is quite nonlinear, so the force between the gear, the teeth, is following a certain angle. So very similar. So yeah, this is like this is a worm gear. Okay. Okay. I need to move on to this part. This is the major part for this course. Like I said, now you know there's some force coming from the other side, and can someone tell me why we focus on the force that is only applied to the tip, not along the pitch circle or somewhere else? Can someone tell me? Why do we do this? Because you know, whenever there's conjugate motion, the force of coming from I should say the force is going to be applied to the teeth at different positions as the teeth revolve. Why do we only do this? Because this is the worst case. If the teeth can survive this case, it can survive all other cases. So for this course, we only cares about the worst case, the worst loading case. This is why, okay? So there's one particular case where this teeth has conjugate connection with the other teeth, and the force comes at the tip. And there's gonna be a force coming from the angle, and you have a transverse component and the radial component. We only care about the transverse one because that force is gonna make this teeth behave like a cantilever, and it could break the teeth. So how do we study this? Because it's having a curved profile. It's not a rectangular cross section. So there's a guy called Lewis. He studied the teeth profile in a dimensionless way. So basically, he modeled the teeth profile in a more general way. So if you use whatever he introduced, convert all dimensions into dimensionless, then you have a standard equation, like one equation for all teeth design, but it's based on some kind of approximation. Here's where he made the approximation. He treat the teeth profile like a rectangular shape. It's like a approximation. And what does this mean? This gray area is describing how the cross section look like. So basically, it's a cantilever in the length of L, just like how tall this teeth is. And you have a transverse force, and also you have T. T represent the how wide the neck is. Even though this part could be wider, but we cares about the neck, because if this thing breaks, it breaks from the neck. So the neck, the length, the width of the neck is being chosen as the model. And also capital F represents the thickness. So basically like I told you, this part is called the face. And width along this direction is called the phase width. So this is basically how thick your gear is. So he modeled the teeth profile as a very simple rectangular cross-sectional cantilever at the upper right corner. So he tried to study this whole thing in a certain way. At the end, the stress inside the gear can be approximated as basically when you compute stress, it's always force over area, right? So this is how much force you have. And over here, there is something F, P, and Y. So what is P? P is the circular pitch, basically the distance from here to the other, the neighboring teeth. What is Y? Y is a ratio between X and P, but with some coefficients 2 and 3. Why do they have this 2 and 3? To remove some of the numbers, some of the values during the derivation. So over here there is a 2 over 3 right here. So if you define a dimensionless parameter y right here with 2 and 3, you can eliminate some of the numbers during the derivation. So at the end, this equation doesn't have any coefficient in the front. So this is like a 2 times of x over 3 times of p. Basically, it's a shape function. It describes the aspect ratio of the gear. X is like some parameter right here. P is some parameter here. So it's a shape parameter. And how do you get this x? Basically, you need to have a perpendicular angle right here, and this portion is x. Don't ask me why. How come they define it this way? I'm not Louis. I just know how he did it, but I don't truly understand why it was defined. How he come up with it, I have no idea. Anyway, if you are able to have these assumptions and derivation at the end, y is dimensionless. It's some kind of length over the other part of length, so y has no dimension. So over here at the bottom, f is the phase width, p is circular pitch, so meter times meter is meter squared. So at the end, this is still pressure. This is Newton, this is meter squared. But it's based on some kind of definition of this dimensionless parameter. So this equation is good for all kinds of shapes. However, this is only the most fundamental way to estimate the stress. It's not accurate enough. So what do? You start to apply coefficients that make adaptive conditioning of the stress. So I'm going to show you the final equation. So what I showed you earlier, that was the fundamental. But at the end, there's a complete equation. Let me show you where. The entire chapter of this book is trying to explain all kinds of factors. But I'm going to show you bending, yes. So at the end, the stress can be computed by W times K, 5 Ks, times P, capital PD, this is a dimensional pitch, F at the bottom, and some parameter J. This book even tells you need to turn to which page to figure out how to compute each K. So when I was a student, when I took the exam, I still remember it was an open book exam. Because for the professor to print out all the tables for you, it's gonna waste too much paper. So they just give you, okay, you can bring your book, open book exam. And everyone is trying to flip the pages front and back, trying to find all the values. Okay, so my goal to teach this chapter is not for you to memorize this. I just want to introduce you what affects the stress inside the teeth. Okay, so everything was based on Lewis form factor, the dimensionless parameter, and then people start to make adjustments based on different factors. And each factor has a meaning. If there's no factors, if every factor is 1, then it's no condition. But in reality, there's several things that you need to consider of in the stress analysis. And how about what is sigma all? So at the end, this is like how much stress applied to your teeth, and this is how strong your teeth is. So this sigma is supposed to be smaller than the allowable. This is not all, this is allowable stress. So this is how strong you are, this is how much load you carry. So in your design, this equation must be smaller than or equals to this equation. And over here, there are also factors. And also the safety factor is here, SF. Okay? So I think I cannot cover all the parameters. I guess I can just quickly go through what are those. And only when you are a gear designer, probably you come back to this book and figure out what's necessary. So one of the factors is about the speed, how fast the gear is rotating. So with different speed, and also V is the velocity. For different kinds of gears, if it's made by casting or made by cutting, the factor behaves differently. If you are interested how come they know the parameters should be tuned in this way, I guarantee you they made tons of experiments and figure out how to tune this. Okay? So if you are a researcher in gears, maybe one day you figure out another factor that should be applied as well. I guarantee you in the literature, there must be some other factors that was done somewhere around the world that was not covered in the book. So I believe there are still some open research in gears. So one factor is about the speed. Let's take a look at some other factors. See, I actually didn't tell you what is this small k. Remember, SE is the endurance limit, right? But in my exam or homework, I always tell you how large the endurance limit is. But actually, there are ways to compute endurance limit. And it has a bunch of 6 different Ks. So that was on the other chapter of the book. I didn't cover it. So this book is filled with a bunch of parameters that was obtained from experiments or models, and researcher have done this years ago, tens of years ago, or hundreds of years ago. I have no idea, and they collect a bunch of equations in this book. So if you have you plan not to spend effort on making your own experiments, usually you can follow those equations. And many of those equations were provided by the manufacturer. The manufacturer tried to sell their components, so they have done tons of experiments, and then they try to tell you how to use it. Let's see what are the other factors. Okay, here's the complete equation. So KO, overload factor. Let's take a look at what is overload. KO. I want to introduce you what is all the K's. Okay, let's focus on this one. This is about the geometry. And I remember there's a table of J. Yes. So there's like a geometry factor. It's about the shape. And in this table, here is number of teeth for which geometry factor is desired. And this is number of teeth in the mating, the conjugating gear. So it depends on how your gear is conjugating with the opposite gear. And the number of teeth affects this geometry factor. Okay, you need to match this table to make adjustment. Also, if you have helix angle, basically helical gear, then the factor changes as well. Okay? No, maybe, yes. This one, I want to move on to, okay, this is about the speed, like we said earlier. The dynamic factor is about speed, yes, and overload factor. Basically, the level of loading. If you have uniform force, then the driving system and the power is providing uniform force, then it doesn't make such an impact. However, if you have moderate shock, sometimes there's a certain shock of the driving force or the power, then you need to apply certain factor right here. So usually, whatever factor we applied, that will make our stress values larger. It's just like a stress concentration factor. But it's not about stress concentration. It's about how much stress could be applied to the component. And by this table, in this level, there's 1.25 times greater of stress will be applied to the teeth. That's the idea. Okay. Size factor. So based on different sizes, face width, y, some other parameters, this is a diametral pitch. So there's whenever you see an equation like this with some very weird coefficient right here and also in the front and also in the power, trust me, it's a model that was built based on experiments. They have done a bunch of experiments and they realized, okay, here's a characteristic parameter can be defined in this way, and there's just unknown parameter to be determined. So they have unknown coefficients here and here, and then they did a bunch of experiments at the end is based on model fitting. And so those numbers usually are numbers determined by model fitting. Okay, load distribution factor. So if the force applied to the teeth is evenly distributed or not evenly, then there's a factor. Okay. So there's ways to compute. You know, for the teeth, sometimes we call the teeth looks like a crown. So if you take a look at the picture on the upper right corner, the dashed profile is the original profile, but they make the teeth profile a little bit rounded. So it's called a crowned tip. So if the profile is a little bit crowned, basically on the edge, it's slightly smaller than the original shape. Then you will have more load applied to the center because greater force being greater area being contact with each other, the opposite side. So that means your load is not going to be applied evenly at the entire profile. Okay, then there is a distribution factor. Okay. Let's take a look. Some other factor. How hard of the material you are using. So basically, they study the ratio of the hardness of the pinion and the gear. So if there's a difference between the hardness, then you need to apply certain factor. Cycle. So whenever you talk about cycles, usually you'll talk about reliabilities. So they usually define how reliable your component is after a certain amount of cycles. And usually it's in the power of, to the scale of 10 to the power of 6 or even greater. In this case, the standard provides values in the 10 to the power of 7 cycles. So over here, this is just like the profile that you usually see for endurance limit. So usually you have a strength, and after a certain amount of cycle, the strength drops. Very similar to that kind of idea. But over here, there's a point right here. The strength doesn't drop too much more after a certain amount because the material usually after a certain amount of cycle it reaches to its endurance limit. The strength doesn't drop anymore. So over here you have a deeper slope, but afterward the slope is not that deep, not as deep. Okay? And researcher has done experiments and then fit the models. Over here you again see those numbers, very strange numbers, coefficients, they're models. Okay? Like I said, and also reliability. Are you looking for 99% safety, or are you looking for 90% only? So for different safety level, you apply different factors. Okay, so what usually, when we talk about reliability, what does it mean? Usually it's like after a certain amount of cycles, if your reliability is 99%, that means if you have exact same gears, 100 pieces of them, one gear will break. That's 99%. If you are looking for 90% only, 10 out of 100 will break. something like that. But usually it doesn't break when it's brand new. It's usually talking about the reliability after a certain amount of cycles. And usually the data provider will let you know what does it mean. And it really depends on how they did the experiment earlier. So when they provide the information, it's based on the statistics from their experiments. Okay, and also you sometimes have gears, so-called the ring design. It's like a ring. So this part is called the rim. If the thickness of the rim is too small, it will affect how strong the entire gear is. You know, the entire rim will be bending a little bit. And also safety factor right here. Combining all these, you have equations like that. There's actually another part of this analysis. It's called the contact stress. This is how you put all the equations together. So whatever stress you have must be smaller than how strong your model is. Okay, this is so-called surface wear. Also studied in stress, in the unit of stress. It's called contact stress. So because you have two mechanical parts or components conjugating with each other, and you have force transmission between each other. So if too much force is applied, it could break. And there are two failure modes. One mode is to directly break the teeth. When the transverse force is too large, you treat it like a cantilever and it breaks it directly. And actually, for this kind of conjugate motion, you have highly concentrated forces at the contact area. And over that area, there is contact stress, like a concentrated stress. And sometimes it will generate surface wear, but not break the entire teeth, just surface wear. So surface wear is another kind of failure mode for the teeth. And their researchers focus on the surface stress. And these are the equations for the surface stress. This is how you compute the surface stress. This is the allowable surface stress. And as you can see, there are so many coefficients as well. Some of them are the exactly same coefficient, but there are some other coefficients. I didn't pay attention to surface stress for the entire course, so I plan not to talk about those. However, I need you to know, in the future, when you are designing for a gear, if you are truly trying to choose a gear and study how long this gear is gonna last, you cannot just treat it like a cantilever and just make sure if it's going to break or not. You also need to think about the wear at the surface. Because if you have surface wear on the teeth, then you don't have a smooth connection with the opposite gear. Okay? So I recommend you come back to this book in the future when you are designing gears. Okay? So that's everything about this chapter. The other chapter is about bevel and worm gears. Basically, it's gonna cover the stress analysis for bevel gears. It's even more complicated. I just want you to know there's a chapter about this. So I think I can just move on to the overall equation again. This is about the worm gears. Again, the Lewis form factor, similar approach. This one doesn't have it. So I think that's pretty much I want to cover for the entire gear design. And the key information about gear design is that when we design gears, you need to know how much force is being applied to the gear, and if something is gonna fail, it's gonna be the teeth. Whether there's surface wear or maybe the teeth could break. And also, due to those forces between the teeth, the shaft is gonna carry reaction forces. So when you study for the entire shaft, whenever there's a gear, then there's reaction forces right there. Okay? And I think in almost every machine, if there's a shaft, usually there's a gear. So this is so common. So take this one as an example. This is a very common design. You have a shaft, and usually the center part is larger. Why is that? Because you install the gear from one edge and then the other edge. So there's a corner where you can stop the gear. And usually there's a key, and when you install the gear up to here, you find a way to fix it, to fix it. Maybe there's a bolt or some other, or maybe there's a bolt here, and there's bearing. So gears are so common, and this is a pulley, right? Because why do we have shaft system in a machine? We usually want to drive the machine. You want something to move. And one common way to make something move is to use a motor. And motor basically spins. So one easy way is to use the motor to drive a shaft, and whatever you want to move will be connected to the shaft. And gears are one way to drive the force. Pulleys is another way. If you can use gears, that's good because they are rigid parts, tightly conjugate, mating with each other. There's very little backlash, so you have little loss of energy, and you have very little flexibility of motion, so the movement can be pretty precise. If you use pulley, it's based on a belt. It's a flexible part, so there's room for a deformation. So if you use pulley and belt, it's simpler because you can have a longer belt. Your driving axis could be here, your driven one could be far away, and you use a belt to hook them up. Then you don't need to have a lot of components between it. However, the belt is flexible, so a belt and pulley could be less accurate. If you want this to be accurate, then you want a stronger, you want like a tighter, like a more rigid material. then maybe you want to use a chain. When you use chain, then you have issues. Like in your bicycle, you have chain, right? And sometimes chain jumps out of your jump out of the teeth. Then you need to figure out a way to put the chain back to your bicycle. So every kind of mechanical part has its own strength. Gear, of course, is very strong, but if you want a driving force here and a driven force at far away, then you may need to have a lot of gears, right? Then you need a lot of shaft. That's gonna be costly. Okay, so that's it for today. Any questions about today's lecture? Okay, there are many interesting things about gear design. This book has 3 chapters about gear design. The most content in the book. So I still recommend you to get a book in the future, because as a mechanical designer, I think it's going to be useful at some point in the future. So if you can buy a book, you can go and get a used one, use it as a tool book. Okay? That's it for today. I think we should check the attendance.
在下面图，
Okay.
最下面。
This one.
Yes.
So please scan the QR code for attendance, and then that's it for today. Tomorrow we have our final round of interview. Last time some of you didn't come, so tomorrow is the last chance for you to do the interview. If you missed previous interviews, come tomorrow, talk to the TA, okay? The interview counts as your part of your score, so I plan not to do makeup for interviews. So tomorrow is the last time. After tomorrow, if you miss it, you don't have it. You don't have the interview score. That's it for today. Okay, bye.